to give this talk a second time. So we had problems, multiple problems last time. First, the meetup was broken, and so a lot of people couldn't get to the talk in the first place. And then Zoom failed to record the presentation. So I'm very appreciative of Tom for volunteering to give his time and give the talk a second time. And so I'll turn over to Tom.
All righty. Yeah, I'm not muted. Good. So yeah, thanks everyone for joining. As Dave said, this is sort of a rerun of a talk I gave a few weeks ago. Basically, I'm just going to go over the details of a clock. Really, nothing much more to it. Well, I might say that, but yeah, just going to go over the details of the hardware and software and like the sort of effort you can go to, I suppose, to yeah, just to tell the time. So let's get into it. Oops. There we go. So yeah, basically the origins of this sort of clock basically start back in 2017. Actually, I built another clock which was built entirely out of NOR logic, and that was inspired by the Apollo guidance computer of all things. I used about 1,500 transistors in that clock, basically forming open drain gates. And NOR is, if you're sort of familiar with it, NOR and NAND are essentially what they call universal gates. You can form any other kind of logic just through a combination of the right gates using NOR or NAND. And back in the time when the Apollo guidance computer was built, NOR, I think, just happened to be one of the most reliable, or perhaps maybe the most available logic gates, you know, that sort of existed. And they used sort of one universal type of gate in that that computer. It was a triple input NOR gate, and they just used it, you know, in whatever combinations they needed to in order to you know, to form the logic for that computer. This clock took me about 5 months to build full time, or nearly full time. And when I say nearly full time, I sort of mean like, you know, come home from work, do a couple of hours worth of soldering. On weekends, you know, a few hours more. You know, it was a pretty big effort, and the result of all of that is essentially a clock that could display sort of like time and date for a single time zone. Things like daylight savings times and leap years were all handled manually. Like if you know, used to ever having to adjust a clock, you know, forward and back for daylight savings time, you know, maybe skipping a day or something during a leap year, you know, it's essentially that kind of thing. You know, it's all literally, you know, everything is defined in hardware about how this thing works. And one of the big drawbacks of that clock is that it's probably pretty impossible for almost anybody else to build, just because of how it is. And you can kind of see this image I've got on the screen here as well, which is just one of the boards out of this clock. You know, it's all individual transistors with, you know, some resistors to form all the gates. You know, it's really a lot of work to solder it. And, you know, with 1,500 transistors, you know, you're talking thousands of solder joints. And like, I think I went through about 100 meters of like 30 gauge Kynar insulated wire to sort of hook all of this together. So it's not particularly sort of, you know, something that anybody else might want to build even, perhaps. I mean, it's a pretty cool little object to have, but yeah, it's not very repeatable. So after completing that and having sort of embarked on my, you know, sort of retro computing style journey, I suppose you might say, I started to sort of think about a new clock that I wanted to build, and, you know, what sort of things would I want in that clock? And well, I guess the first question is like, why build another clock? And well, you know, they are kind of useful. You know, the time and clocks sort of, you know, govern a lot about our lives. It sort of determines when we, you know, when we wake up, when we go to bed, when we go certain places, when we eat, and all that sort of thing. So, you know, it's got a purpose. And goal-wise, I'd always wanted to do something with the Z80 processor, and that kind of goes back to my childhood when I first sort of learned about, you know, the fact that Z80s even existed in the first place, and that was from a model railway magazine of all places. There was a project in there. I think it was maybe something like a signaling control system or something, but I had no idea really what I was looking at the time. I was far too young to sort of really understand it. I lived on a farm in Australia, so access to information or people who knew anything about this sort of stuff, was difficult, to achieve, or, to make contact with these people. And so basically from learning about, the existence of this thing called a Z80 processor, I kind of always had this idea, like I want to do something with this one day. And it's maybe also a good sort of time to sort of give a quick, explanation of my sort of interest in retro computing in general, which is not really so much about retro systems. It is more so like the retro hardware. I mean, I had a Commodore 64 when I was growing up, but I never really knew what it was. It didn't mean anything to me back then. It was like it was the first computer we ever had. We didn't have a tape drive or anything for it, to be able to store and load programs. We had a couple of games on cartridges, but it didn't really mean much to me. Like the concept of Z80 versus 6502, certainly I had absolutely no knowledge about. So yeah, I wanted to build a clock, or I wanted to do something with the Z80 processor, and I thought this could be a really good opportunity to actually to make good on that sort of bucket list, wish list kind of thing. So I thought, well, the last clock was sort of one time zone, which is all well and good, but being a network engineer, I'm sort of used to the sort of stereotypical view of a knock, with multiple clocks, times from around the world. So I thought, well, why not build a clock with multiple time zones? And I thought realistically I can probably fit 3 on there on the display. So let's aim for 3 different time zones. And whereas the previous clock was sort of a hardware problem in terms of displaying times and dates, this was going to be more of a software problem. So it seemed more achievable to do something like 3 time zones. The other clock used the mains frequency as a source of timing, or here in Europe we use 50 hertz AC, so all I need essentially is a divide by 50 sort of counter to give myself a 1 second interval. In in America and other places it will be 60 hertz, but yeah, so sorry. So yeah, instead of using the mains frequency as a time base for the clock, this time I was going to use an actual real-time clock. And another advantage of using a real-time clock was going to be that if the power was to be removed, it would actually be able to keep the time as well. So the other clock, when you remove the power, you turn it back on, it's all zeros. So you've got to basically go through and reset the time and the date, which is like, well, fortunately where I am, I don't seem to have many power outages. So the only time I've ever had to do that is if I've had to move it myself. So, but it's a little bit of a pain. So yeah, use a real-time clock to maintain the time when the power goes away. And then I also definitely wanted to be able to adjust for daylight savings time in software this time. Well, it was going to be a software thing. Just because it's more convenient to be able to do that, and displaying multiple time zones. I don't really want to have to know what, when daylight saving starts and ends in various time zones around the world. I just want that to be all taken care of for me. A bit of a side effect, I suppose, maybe of the real-time clock that I'm using is that it handles leap years for me. But handling leap years was also, automatically was a goal that I wanted to achieve. Just, less manual intervention and more automation. I also wanted the character set to be customizable this time. In the other clock, everything is like literally hardwired. You take some inputs from basically a bunch of BCD counters, for things like the time, day of week, the month, and all that sort of thing. And then you've got to translate that into a series of outputs to drive all of the various segments on the displays. And once you've sort of determined what your characters look like, and you go and wire that all up, which is what I had to do, making a change to the style of some letters or characters or whatever is very difficult to do. So I wanted that to be able to customize the character set that gets displayed simply by reprogramming a ROM was a big sort of want in this clock, because I made some decisions with the other clock about how some characters would be displayed, and I sort of thought, well, I don't really like that anymore, and I'd prefer to do it a different way. So this was like a pretty big sort of item on my wish list. And then obviously customizable time zone. So I don't really want anything hard coded. So I came up with essentially my own sort of little TZ database format, just some basic description of the time zone and its offsets plus or minus from UTC, which is sort of the base time that you configure the real-time clock to display, and then everything is sort of calculated as an offset from there, and that is all stored in a ROM. So you can add time zones, you can remove them, call them what you want, give it whatever offsets you want. And display dimming. You don't want this thing like running at full ball or full brightness, if you've got, say, it's in a bedroom and you're trying to go to sleep, you kind of want some darkness. So the ability to dim the display between certain hours was obviously, it's quite a big sort of important thing. And it's the one feature that I'm basically missing from my other clock. I've sort of got, it's been on my to-do list for quite some time now, but understandably, I just haven't really found the time to sort of sit down and wire up, maybe another 100 or so transistors required to sort of implement some display dimming in the other clocks. So again, this could be done, either through hardware or software or a combination of, and in the end, it sort of ended up being a software thing, but I'll get into all those details a bit later. I wasn't going to worry about any sort of alarm functionality. I use my smartphone as an alarm these days, and that does a good job. And I don't really need or want it in another device, so I didn't worry about any of that sort of functionality. And another thing I wanted to achieve was to make it more achievable for other people to build. So not having to solder together, 1,500 transistors, if it's 20, 30 or so standard logic chips and other bits and pieces, it's a lot more achievable. Just purely in the amount of components alone, let alone anything else. So those were all kind of like the goals that I wanted to try and achieve for this next clock. So I started sort of in early 2019 by putting together basically most of the hardware. I did a lot of the designs. I built a lot of the hardware as well. And I got it to a stage where it was actually, functional enough that I could start playing around with software and display driving routines and that sort of thing. But then I started renovating my house. And that has essentially ruled my life for the last, well, things are better now, but, the best part of a year and a half, I've sort of been reasonably busy, renovating the house and fixing things up and, running out of energy to really do anything else. So for basically the whole of 2019 into early 2020, it literally kind of sat around and just gathered dust through all of these renovations. And earlier on this year, despite what was going to be the pandemic, I made a trip back to Australia, and I sort of took it with me. And I thought, I'm going to be out there for a few weeks, and this will be a good little project to work on, and I might actually be able to complete some quote unquote of the software development. But just as I was preparing to sort of fly back towards the end of March, the whole world kind of went into lockdown, and I got stuck out there for, well, essentially an extra month and a half over what I was initially meant to be there. And through that time, obviously gave me a lot more time to work on this. My employer wouldn't allow me to work while I was out there, not even remotely. So I basically had an extra month and a half of free time to be able to work on this. And yeah, in that time, I actually managed to get it to a very complete sort of state. Just sans one or two little things, which I essentially was waiting to get back to the UK, where I had all of my tools and stuff, and I could make some changes, make some fixes, and add a couple of little things here and there. So yeah, by the time I got back, it was actually quite a functional thing, and I'd been using it, as a clock while I was out there for, the last couple of weeks, giving it, a bit of a run and taking it through its paces and making sure it was reliable. And we had a couple of, I think we had a transition between sort of daylight savings and non-daylight savings, or the other way around. I still get these two confused, but yeah, so that sort of gave me a bit of an opportunity to actually see it in action, changing between sort of daylight savings and not daylight savings, and making sure that was all working fine beyond the testing I'd done. So yeah, basically now we kind of get into the how bit. And I'm going to sort of break this into two sections. One will be about the hardware and just what sort of, what's involved on the hardware side. And then towards the end, we'll do like go over the software and the development environment and all that sort of thing, like how it's all laid out, the architecture and other little bits and pieces that I've sort of built into the software to help me achieve this. All right, so the clock is modular, and it's made up of several boards, and each board kind of provides a different function or does something in particular in the clock. I'm using an RTC and like a Z80 CTC chip to generate all of my interrupts, which I used for like refreshing the display and also updating the contents of the display. The display driver itself is basically just a big shift register. And I debated a bit in my mind about whether I would use a shift register or maybe just like a series of latches to hold all the bits and turn on various segments. And in the end, I sort of settled on a shift register because it sort of also gave me a bit of an opportunity to build something I'd been sort of thinking about for a while, which was like, how would I implement like the driver portion of a shift register? So that gave me an opportunity to have a go at that. And the display is multiplexed on sort of a row by row basis. So the shift register is basically big enough to be able to hold all the bits to drive every single segment on one row of the display. And we'll sort of go into a few more details about that. So yeah, starting off, we've got the CPU board itself. It's basically I guess a single board computer. We've got a processor, we've got some ROM or ROMs, we've got RAM, bit of logic here and there, we've got a power entry, oscillator for the clock, for the to run the CPU, and some reset circuitry. The reset circuitry is actually it's not a 555, even though it's a little 8-pin package down there, but it's like a voltage supervisor. So it'll hold the CPU in reset until the voltage rises above a certain level, at which point it will release it. But it also, like using a resistor and a capacitor, you can set sort of like an RC time constant almost to sort of generate a pulse. So if I push the reset button, it's, it'll generate a pulse. I think I've got it set at about 200 milliseconds or so. So it kind of, in a way, like debounces the reset button and provides just a single, reset pulse to sort of reset everything back to defaults. So this is sort of the layout of the CPU board. The two ROMs up in the top right-hand corner, the little PLCC packages, one of those is the character ROM, and the other one stores all of the time zone data. I don't remember exactly which way they are. I think character ROM is the very right-hand one, but it would also be possible to do all of this with a single ROM. I just sort of thought for, you know, ease of prototyping, that sort of thing, you know, I can just pop out whichever ROM I need to change. But you know, yeah, it's certainly possible to fit all of this into one ROM. You can sort of see, like over on the left, I only ended up using about you know, 5.5 kilobytes out of you know, what is actually technically a 1 megabit ROM. So there's plenty of space to hold it, and still plenty of space, you know, even in the memory map, you know, to be able to combine all of that into one single ROM. Yeah, so that's the front side of the board, and then the back side of the board, if we'll proceed, yeah. I've chosen to go with rat's nest construction, and this is sort of my preferred prototyping method these days. I've also tried using VeriWire. If anybody else has tried using that, you sort of you know, lay down these little comb structures between all of your chips, and you know, provide ways to sort of route all of your, like, the wires around your board. But trying to troubleshoot something like that afterwards is very difficult. You know, once you've got a bunch of wires running in the same direction, trying to trace one of them out, you really need to be looking at your schematic. Whereas obviously, you know, with this, you know, you can just sort of pick around with a pair of tweezers or something and just, you know, follow the wires along. You can add more in quite easily, make changes very easily, and that sort of thing. So I've sort of decided, yeah, to sort of stick with this construction method for strictly, you know, raw prototyping. Obviously, you know, another method is, once you've done this kind of level of prototyping, you can obviously then go to PCBs, but I haven't quite gotten that far yet. And the color scheme I'm using for all the different wires here is yellow is for the address bus, green is for the data bus, pink is sort of all of the CPU control signals, and blue is sort of just like generic, you know, logic and signals of various sorts, chip selects, things going between and OR gates and whatnot. Red and black obviously are your +5 volts and ground. And moving on to the next board is sort of, if the CPU board is the brains, then this is kind of the heart, I guess, of the clock. So, you know, this board here sort of provides all of the user interface, so switches and buttons. We've got the CTC, which generates, you know, all of the different sort of interrupts that the clock uses, and one channel of the CTC is used to sort of vectorize the interrupt from the RTC. So the RTC, obviously not being a Z80 family peripheral, you can't sort of, you know, you basically got to just poll, you know, to find out if it was that device that caused an interrupt. Whereas if you sort of hook that into a Z80, like a CTC channel, configured as a down counter, load the channel with a value of 1, then when the RTC generates an interrupt, the CTC channel decrements to 0 and then raises an interrupt, and will then be able to supply a vector, which you can then use to sort of branch straight into the code that you need to, you know, service that interrupt. So that's quite nice. That's a little trick that I learned along the way. There is a little speaker. Although I said I wasn't doing any alarm functionality, I did actually build in a little speaker. I thought, you know, maybe I'd have some beeps when you press buttons, or maybe like a little blip, you know, every hour or something like that. But I haven't quite sort of figured out really what to do with it, or even, you know, the best way to drive it. There's a bunch of latches on here. I think it's mostly those the chips on that row in the middle, which are sort of used to read all the buttons and the switches. And there's also one used for output. And the speaker is sort of currently hooked up to that output latch, so you can drive it through software. But I do have one channel free on the CTC, and I'm sort of thinking, well, maybe it's probably better to actually hook it up to that, and then you can sort of drive it at, you know, any frequency, and it doesn't, you know, necessarily have to consume quite a lot of processing power to do that. So yeah, that's still a bit of an open sort of, yeah, decision to be made yet. And the real-time clock actually also has some watchdog functionality in it, so it can yeah, cause a reset if you sort of don't, you know, poke that watchdog, you know, frequently enough. So there's a little jumper next to the RTC, which, because it's an open collector signal, you know, I can just move that jumper or remove it if I want to enable or disable the watchdog functionality, or at least the reset portion of it anyway. The oscillator on this board was originally used to sort of provide input to one of the CTC channels, because I was sort of working under a, you know, an idea of wanting to have a really, really precise timing interval for sort of scheduling the main loop. But I sort of didn't end up using that in the end, so that's kind of just chilling out there, not really doing anything at the moment. And that just basically hooks in through a, I think it's an 8-bit counter, so I could, you know, sort of choose from a whole array of different, you know, timing outputs, I suppose. And again, backside of this board, we have rat's nest construction, the same sort of color scheme as the CPU board. Yeah, not not really much else to say about it other than, yeah, it's it can get quite messy in a way, but yeah, you can at least follow everything quite easily. So yeah, and that brings us on to the display driver board version 1. So as I sort of hinted at the beginning, it is basically just one big shift register, and in particular, it's 136 bits. 128 of those are used to drive the display segments, and then a further 8 are used for the dot points on each of the displays. So you do sort of have the ability to use all of the you know, segments and whatnot. You just have to shift out the right data. Version 1 used a sort of the discrete sort of parallel load to sort of serial out shifter that I was sort of wanting an opportunity to kind of design and use. So that's sort of mostly comprised of the sort of standard logic chips on the bottom row there. And basically it just presents an interface to the CPU where you can simply out a byte to the address of the shifter. And once you're finished with the IO write operation, it takes the data that was latched in and then just sort of shifts out 8 bits and then sort of stops and waits essentially for the next byte to be shifted in. Or you then, you know, if you've shifted out all of your bytes to set up the new data for what needs to be displayed, you can then write to basically a control latch and essentially set which row you want to then display that data on. And the act of sort of doing that also serves to latch in the data from the sort of shift register into the outputs of those shift registers. So, you know, you can sort of shift in all of your new data, get it staged, get it set up, and then the very last thing you do is write and say, like, I want to display this on line 3, and then that will sort of, yeah, latch in all that data and then switch the display over to line 3. So then line 3 will then be displaying the data that you've shifted in. It is write only, there isn't anything to read. I did sort of contemplate, you know, using another shift register to sort of give myself an ability to read data that had been shifted through, but I didn't really see, you know, other than maybe some kind of diagnostic when you're starting up, I didn't really see any kind of benefit or advantage to actually implementing that, so I didn't do it in the end. And version 1 used 74HC595s for the shift registers, and as you can see, there's an absolute boatload of resistors, because these are all the current limiting resistors that you need to, you know, for driving each of the display segments. So it's, yeah, it's common sort of off-the-shelf parts, I suppose, you know, things that you might have laying around if you play around quite a lot with this sort of stuff. But yeah, adding an extra 136 resistors that you need to solder in is not that great. And backside, yeah, again, rat's nest construction. And this time I've sort of added a new color to my wiring, and the orange ones are essentially each of the signals for driving the LEDs. Yeah, quite a lot of them. Excuse me, I just want to take a drink. Yeah, so you can sort of see like this. It takes a bit of time. Like I think it took me about maybe 2 nights or so worth of soldering to get all of this put together. It's quite a lot of work, but it's not too bad in my opinion, if I do say so. In terms of prototyping, it actually seems to work quite well. All right, and then this brings us on to sort of display driver version 2. Yes, I did go through like an iteration with this one, and basically I sort of wanted to fix, I suppose, some of the mistakes you might call them with version 1. Although it worked perfectly fine, I also sort of wanted a bit of an excuse to do something with a CPLD, because this is kind of my latest sort of pet project, is sort of playing around a lot more with programmable logic. The little PLCC package in the middle there is an ATF 1502 to 32 macro cell CPLD. I wrote all of the, well, I don't know if you'd call it code, but all of the logic for that is defined using the Kupl language. If you're old enough in this industry, you might have memories of using Kupl, and maybe in particular the tools WinKupl, which you can sort of download from. Well, I guess it's a microchip now, but you can download that for free now, and it's functional. Like it's got bugs and it's got quirks, but you can get used to them, and you can recognize the signs, and understand, okay, I need to restart this and work around this bug that it's got. Because for example, sometimes it will just basically, if you're trying to simulate your design in WinSim, like it might just completely stop updating results, and you go, well, I've made some changes to my logic, but it's not reflecting these changes now. And then you kind of just get this feeling, oh, okay, well, let's just like close WinSim and restart it, and then you hit the button again, and like, yeah, okay, now it's working again. So yeah, it's not bad. I sort of liken Kupl to assembly in a way. You're sort of really at a lower level than something like VHDL or Verilog. You're sort of defining at a much lower level exactly what the hardware is doing. And so I implemented into that all of the shifter logic, so removing a lot of discrete chips and then sort of squeezing them all into, well, not squeezing, but putting them all into some logic within the CPLD. And then the other change I made, and you might notice the distinct lack of resistors this time, is to use some actual proper LED drivers. So I used the TLC 5916 LED driver, and the big advantage, I think, of those is that you basically only need one external resistor to set the current for all 8 of the outputs. I guess it just uses some sort of current mirror, to sort of replicate, that whatever sort of current setting you want for each of your outputs. They still function as shift registers. And so the functionality of this board is exactly the same as version 1. There's no software changes that need to be made to support this board over the other one. You just out a byte to the address. Once the IO write operation is finished, then it just shifts out 8 bits. And then the same thing for the control logic. You write out which row you want to display. That latches all the data in, and then it turns on whichever row you've asked for. So yeah, that sort of, I guess, modernized a little bit and removed a bit of the excess sort of construction that was needed for the other board in terms of components. But it doesn't remove the excess of construction on the backside of the board. So it's it's still very similar, you know, just lots of wires, you know, rat's nest construction and that sort of thing. So yeah, it fixes one problem, but not the other, but anyway. And then next board is, I guess, you know, the bit that you look at, so the display board. You know, I've managed to fit 3 rows on there. And each of the displays is basically a 16 segment display. There's 8 of those per row, so that's what gives us the 136 bits, because 8 times 16 is 128, and then a further 8 for the dot points themselves. And as I mentioned before, everything is sort of multiplexed by row. So when we go to the back side of this board, you can sort of see that everything is kind of arranged, or the wiring is all arranged in columns. So, you know, segment A is connected to segment A on each row. And then, yeah, basically some little transistors down the bottom there in the middle. PNP transistors will turn on based on which row you've sort of written into the control register on the other board, on the driver board. It'll, that sort of, the output from that control register feeds into a 74HC138. And then, yeah, that's provides like a single sort of low going output, which then turns on a PNP transistor and supplies some power to the row that you want to display. So it's a common anode setup, I believe. A couple of small changes have been made to the backside of this board. You might maybe just barely be able to see that there's some thin red wires sort of mixed in amongst all of the orange wires, and they're sort of like the power supply for each of the rows. But I did sort of notice that as the display was being filled up with characters, you could sort of see it getting dimmer and dimmer and dimmer. And I guess 30 gauge wire is not that great at carrying lots of current. So I modified that to use some thicker wire, and that sort of helped that situation a bit. It's still not perfect, but yeah, I suspect maybe the next thing to try would be perhaps some more beefy transistors for driving the road, because these little tiny, you know, TO92 ones probably, yeah, they probably also struggle a bit as well. But that's the display board. And then the final board is something that actually I whipped it up sort of in the days before I flew out to Australia, and it's just got a Z80 SIO chip on it. And the intention was to use it for software development. I wanted to basically write a small bootloader which would sit in ROM and then be able to upload code over serial link and then maybe execute it from RAM to help with the development process, rather than having to sort of, you know, take the ROM out, put it into a program it, put it back, and, you know, that's quite a tedious sort of process when you're trying to do some maybe rapid development. But yeah, so it was primarily intended to be used for software development, but I think I'm going to end up keeping it. And we'll probably see if I can somehow hook it up to a GPS module to basically use it to keep the time in sync, because I've noticed that the real-time clock does kind of lag behind a little bit. I think it's sort of like 20 or so seconds behind now since I last set it. So maybe a little bit more software to sort of run, you know, once a day at midnight or something like that. Get the, you know, the latest time via GPS, and then, yeah, update the real-time clock and just sort of try and keep it a bit more accurate. And the good thing about using a Z80 family peripheral is that on the back side of this, it's really incredibly simple. Nothing more than a few address lines for decoding the data bus, and yeah, most of the signals are sort of going off to the 2 headers where I plug in my FTDI cable. So that, I think, basically, yeah, it sort of covers all of the physical hardware. And this is, you know, just a block diagram basically of how everything is sort of hooked together. It's probably very typical for, you know, a retro style computer, you know, with everything sort of sitting on a bus. It's only really once you get to the shifter that you sort of get to serial data. And then that, you know, the shift register essentially then reconverts that back into like, a massively parallel, value that gets sent out to the display board to turn on all of the display segments. So yeah, pretty straightforward, I suppose. And then that leads in, I guess, now to the software itself. So as I sort of hinted at earlier, the software in this is pretty much, entirely interrupt driven. Between the iterations of my main loop, I actually execute a halt instruction because there isn't really actually anything for clock to be doing in between iterations of the main loop. So why not? I mean, I don't know how many people use the halt instruction in their code, but yeah, I thought, well, why not? Rather than just having it sitting in there, sort of constantly looping around. And this might become a little bit more sort of, or might make a little bit more sense when I sort of, get into more of the details of how the software is actually put together. I've sort of got a bit of a concept of tasks and task scheduling to do a lot of the stuff or a lot of the work in the clock software. And each sort of task kind of does a distinct thing. So, I have a task that runs which reads all the button states. I have another task which pokes the watchdog. There is a task which is implemented to sort of implement some, fancy little effect on the display when it's updating it. And then within sort of the definition of a task, I sort of have two classifications, I suppose you can say. So I've got tasks, which are sort of things which I guess you can, schedule and unschedule as you need them to be run. And then I also have applications, which kind of you schedule once at the start, and in theory, they never really get unscheduled. So there are two basic applications within the software. One is the clock itself, so displaying the times and dates. And the other one is a configuration application, which allows you to set, the date and the time. And sort of the way that all of these are sort of orchestrated is through some sort of locking and signaling constructs. So things like mutexes and semaphores. So mutexes I use essentially to determine like which application owns the foreground. So, and when an application owns the foreground, it's sort of allowed to write to the display buffers to update, whatever's being displayed. It, can or should pay attention to the buttons, things like that. So essentially only one application can be running at a time, because based on whether or not an application owns the foreground mutex kind of also determines whether or not that application runs each time the main loop executes. And then semaphores are sort of used for signaling between tasks and things like that. So as an example, each time the main loop needs to be scheduled and an ISR, the ISR for that sort of executes after an interrupt is generated by the CTC. That ISR will essentially set, a bunch of semaphores or reschedule a bunch of tasks based on, what needs to happen. So yeah, that I sort of went, I guess, to the extreme of sort of implementing software for this thing. I'm using interrupts, I'm using the shadow register set within interrupts. So I'm not nesting any instructions, and it's interrupts, and it's really just more of a simple way to kind of quickly switch into the ISR and back out of it. So I don't have to worry about backing up the registers that are being used in like an application or a task. The interrupt can just fire, it can exchange the register set, and then go about doing its business, swap them back, and then return from the interrupt. And as a result of doing that, like nesting interrupts would then become a very difficult thing to achieve, because you would have to sort of determine, okay, like have I switched to the other register set already? Do I need to back up any registers? So, and to be honest, there really aren't that many interrupts going on anyway to really need to worry about. So yeah, the main loop is executed once every 10 milliseconds, generated by an interrupt from the CTC. So as I was saying before, like on that 10 millisecond interrupt, things like the button reading task will be scheduled. You know, maybe the watchdog poking task will be scheduled, and the display updating or like the display effect task, like those things will get scheduled to run, and maybe no, so the display refresh, which happens once every millisecond, that's actually implemented entirely within the ISR. So when that interrupt fires, that code runs via the ISR directly. So, you know, it doesn't like schedule a task or anything. And that is, I guess, just in essence designed to reduce the amount of jitter or perhaps, you know, some flickering that you might see on the display if something else happens to be running, you know, before it's able to, you know, run the task to go to the next line or next line of the display. And yeah, the software is written 100% in Z80 assembly, as you know, as is natural. This is a bit of a diagram, I suppose, of how all of the software kind of fits together. So like if you're sort of interested enough to go and have a look, because all of the sort of design files, the source code, etc., are up on GitHub for you to browse through. And if you really want to attempt to build one of these yourself, you're more than welcome. So if you're going to go and have a read through the source code, this might sort of help you to understand like the flow of everything and how it's sort of fitting together. So we basically start, you know, from a reset by sort of jumping into a processor test routine. And I sort of actually took this from the IBM 5150 BIOS. It just sort of seems to exercise all of like the various registers, all the flags, you know, if I do something and it should set the carry flag, did the carry flag get set? Can I write a value into a register and can I pass that through all of the registers and will it come back out, you know, unaffected on the other side? So that sort of, yeah, just sort of, I guess, allows you to test that the processor is actually working. It probably doesn't really actually matter these days. You know, I guess manufacturing techniques and whatnot are sufficiently advanced that, yeah, these sorts of, you know, failures might not really happen anymore. Which is actually a nice little segue into the memory test routine. The memory test is essentially, you know, it's sort of like a store, read, compare thing. So like I store a value into a RAM location, I read it back out, and then I compare it with the value that I wrote and make sure that it's the same. And a little bit questionable actually about whether or not this even works, because while I was doing a lot of development, I was having some problems with some crashes, and yeah, I sort of eventually figured out that I think it was the memory chip that I was using and had obviously some kind of fault with it, because once I swapped it, like that was it, like no problems ever happened after that. But the memory test would always succeed. So yeah, I'm not really sure if maybe that works or if it was just something that the memory test couldn't actually detect. It does write, I think, about 4 or 5 different values into RAM, but yeah, perhaps it sort of requires even more sort of, yeah, more values to be written and read to sort of, yeah, pick out this problem that it had. But yeah, what I ended up doing is I took that memory chip and I sort of drilled a hole through one end of it, and now I can use it as a key ring. So nice little touch. And then, yeah, so from the memory test, you know, by the time you get through the process of a memory test, in theory, everything should be okay. So then we sort of launch into the code and, you know, we start initializing the stack pointer, copying initialized RAM values or from the ROM. I'll get into that a little bit later, but yeah, and then, you know, initializing all the peripherals like CTC channels, the SIO, if you're using it, and that sort of thing, configuring and enabling interrupts, and then scheduling applications and tasks for the, you know, leading up to sort of jumping into the main loop. And the main loop is essentially just, it's almost like you can think of it like a bunch of if statements. So like, you know, if a task has been scheduled, then basically just make a call to its routine to run it. So there's just a bunch of tasks and applications that the main loop will run through and then execute a halt. And yeah, sort of essentially just sit there and wait for the next interrupt. So when I say basically that the main loop runs once every 10 seconds, I mean, in theory, it actually runs about once every millisecond, because whether or not it's the 10 millisecond main loop or the 1 millisecond display refresh interrupt that's occurring, that will sort of cause the main loop to go for another run. But none of the tasks will actually run until they've been scheduled via the 10 millisecond interrupt. So that sort of takes care of that, really. And then so just on the right hand side, I guess I've just got a list of all of the various tasks and applications. So as I was mentioning before, like one of them is the button reading task, and I'm quite proud actually of this particular piece of code. Really, I think it's when you're sort of working or writing something, which is kind of like a multitasking kind of, well, I'm not going to call it an operating system, but a multitasking environment. I think this works really quite well, because what it basically does is it will read the button states, and it will do this like once every 10 milliseconds. So it reads the button states, and then it sort of waits for the next iteration, and then it sort of compares the button state again. So it's doing debouncing, but then once it's recognized that a button has been pressed for at least say 2 iterations of the task, it then sort of presents that button press based on a mask that you can supply into a variable. So the application, for example, can just watch this variable, and it can say, has a bit corresponding to button A been pressed? And once it sees that it has been pressed, it just needs to write a value into another variable, which will essentially then mask out that button press until it's released. So the button reading task is sort of finding like, okay, when has a button been pressed consistently, like it's not still bouncing because of contact bounce and all that sort of thing. And then once it's been recognized by another piece of code, it will kind of hide it. So then the next time that it can be presented as a button press is only after it's been released and then pressed again and debounced. So that makes it really easy to implement sort of like applications, because I just look for a bit. Once I see it, I set a bit just to mask it out and say, yep, I've acknowledged this button, I've seen it. And then, further iterations of the application, like when it starts watching this bit again, like it won't actually see anything until like the user has actually released the button and pressed it again. So that sort of takes care of a little bit of a problem in general that we've all probably had, which is like sort of waiting for buttons to be pressed and released. And then the 2 applications, the clock application, which basically computes and displays each of the times or dates for each configured time zone, and that sort of that is scheduled basically by the real-time clock generating an interrupt once per minute. So actually, I think I've got more details on this on the other slides. I won't go into too much right now, but it's once that real-time clock interrupt has happened, then the clock app will sort of go through and do 3 iterations of a loop, which then sort of calculates, based on UTC from the real-time clock. It'll apply all of the offsets, plus minus however many hours, or haven't done minutes yet, but it wouldn't be too difficult to do that. But plus or minus however many hours for each of the time zones, and then actually it will do sort of a second iteration of that loop if a time zone is currently in daylight savings. Then it will go sort of for a second pass and add on 1 hour, And it's sort of like a bit of an iterative thing. So it'll add on however much time, and then, you know, so it'll add on X number of hours, and then it's got to work out, have I gone over 24 hours, and then do I need to increment the day? And if I've incremented the day, like, have I gone beyond the end of the month? So do I need to increment the month? And, you know, it's quite a bit of a, if you've ever tried to write this kind of code before, it's actually, you know, quite an interesting challenge to sort of, yeah, to make that work. But at the end of it, it basically is computed 3 time zones, and it will update the display buffers if you know, if it's actually running, yeah, to display, you know, whatever the new time is for each of those time zones. The configuration app, as I said, is just basically allowing you to set the date and the time. And this is setting the date and time of the real-time clock, which is specified in UTC. So you don't set the date and the time for each of the individual time zones, just the base time of the clock itself. The display task is implementing a little effect, which I can demonstrate after the presentation. But if you've ever seen any videos of the DISCI interface that they used in the Apollo missions, the command module and that sort of thing, and you can kind of see as the display is sort of being updated, you can kind of see each of the characters sort of, you know, being updated one after the other. So you get this kind of, yeah, jumbly kind of effect of, you know, various bits and pieces of the display updating. So I've kind of replicated something like that to update my clock, and it looks quite nice actually. It's a neat little effect. And then, yeah, like a task that basically just pokes the watchdog. So that's just implemented by doing a read or a write to a particular IO address, and then the you know, there's like a magnitude comparator sort of, you know, address decoder type thing going on, where it just sort of, you know, the effect of sort of reading or writing to that IO address just kind of causes its output to toggle, and then that, you know, feeds into the watchdog input on the real-time clock, and then resets its counter. And then this is sort of a bit of a overview of the interrupts that I'm using. So I'm not using the non-maskable interrupt at all. You can't disable it, and to be honest, there's nothing really going on in the clock that needs, you know, sort of instant access, you know, to an interrupt anyway. And because I'm using interrupt mode 2, the regular sort of interrupt vector is sort of unused, and then, you know, that's all done in favor of, you know, having everything vectorized. So channel 0 of the CTC is currently unused. That's one that maybe I could use perhaps after a little bit of rejuggling, but you know, perhaps use that spare CTC channel to drive the little speaker instead. Channel 1 is currently doing the 1 millisecond interrupt to sort of refresh the display, and I sort of distinguish refresh and update, as refresh sort of shifts out the next line of data and then progresses the display to the next line to sort of, you know, cycle through each line of the display. So each line is sort of on for 1 millisecond out of every 3, or, you know, roughly 300 something hertz, I guess, for each for the refresh. It's not too bad actually in terms of flicker. You don't really notice too much when you're looking at it. You might notice something when you sort of, if your vision is kind of moving, you know, you might notice some refresh, but it runs pretty quickly and it's quite smooth to look at. Channel 2 does the 10 millisecond for the main loop, and then channel 3 was used for vectorizing the interrupt from the real-time clock. So the real-time clock is sort of configured to generate an interrupt once per minute, and this process sort of involves a couple of semaphores as well. So when the clock application is running, it kind of signals to the channel 3 ISR. It sort of, you know, it sort of sets a semaphore and says, like, I would like to know when, you know, the next per minute interrupt occurs, and then the channel 3 ISR can kind of reciprocate by saying, like, by setting another semaphore and saying, yes, like, this interrupt has just occurred. So that kind of is sort of like a bit of a synchronization between, you know, the ISR for, you know, the permanent interrupt and the clock. So that's sort of how the clock application kind of gets a signal to say like, yep, go ahead and recalculate all of the 3 rows of the display. So that sort of piece of software only actually runs like once per minute rather than continually, like every single loop. And yeah, a little bit of information now about the development environment that I was using. So I used Sublime, the text editor, with a Z80 plugin, which essentially sort of gives, syntax highlighting with some, nice pretty colors and that sort of thing. But this plugin that I'm using also kind of has a couple of hotkeys associated with it. So one of them, which was really quite nice, was sort of like Control B, which is basically just build the software. So that would basically just execute a script, like a shell script or something, which can then run your assembler and produce some ROM images or that sort of thing. But it also had a second hotkey like Control R, which I guess is for run, and I was really hoping to use that with the serial bootloader and maybe use something like the DTR signal to kind of reset the processor, which would then sort of restart the bootloader, and then I could upload the code that had just been assembled and then start executing it. But I couldn't quite get that working with my FTDI cable. I guess the Python serial module I was using doesn't really know how to control it, or there's something wrong with my cable, but I couldn't get that working. So that was a bit of a shame, but it wasn't too hard to just sort of reach around and push the little reset button and then just run Control B and then upload the software. So the assembler that I used is called Zasm, I guess. It's quite a nice assembler, actually. It's got some nice features, like it does all your sort of standard stuff like includes and macros and whatnot. But as I sort of mentioned earlier on, as part of the initialization process, you can actually have like the concept, I guess in C you would call them static variables. So they kind of start with an initial value, and then like I guess some sort of default value that you needed to have, like a variable to have. So if you use like these initialized variables with the Zasm assembler, it will basically place them all, kind of group all of those variables together in one piece of RAM, and then it places all the initial values somewhere in ROM. And then you can write a very small piece of code to sort of copy the values or the data from ROM into RAM, so that when your code starts running, it starts off with those initial values. So that's quite a nice feature. And one of the other ones is like the concept of kind of local variables. So you can sort of wrap a section of code in a couple of labels, like little processor directives, and then it basically allows you to sort of reuse labels throughout your code. So if you've got a whole bunch of loops, you can reuse the loop label rather than having to have like loop 1, loop 2, loop 3, something loop blah, whatever. So that kind of can help to make code just a little bit nicer to read. As I've kind of mentioned a couple of times, I had a few little tools that I use for serial boot loading. So basically just working in concert with a little piece of boot loading code, which would basically receive a little command to say like, start loading some data at X address, and then you just start dumping binary data over the serial cable, and it will place it all into RAM. And then you can also send another command, which is like execute from address X, and then it will just jump to that location and start executing the code. So I could use that to sort of write some code, build it via this plugin in Sublime, and then just run a little command line or command to just to upload the ROM image and then start executing it from RAM. So that sort of really helped a lot with development of the software for this thing. I did try little bits and pieces and debugged and tested using a website, asm80.com. It's not bad. It doesn't use exactly the same syntax, which made it not exactly copy and paste between what Zasm supports and or what I was using in Zasm, and you know, what ASM80.com supports. But you know, it was good. You know, you could put some code in there, compile it, assemble it, and then launch a little debugger and single step through it, and you know, watch all of your registers and memory addresses and see what was happening and make sure the code was actually doing what you think it does. And then, yeah, final little piece is just a little hardware dongle, which basically plugs into the bus connector that was presented at the back of the CPU board. It's just got like a latch and an address decoder on it. So you just configure an address via the dip switches, and then you just write or just like out a byte to it, and it will, you know, display that value in binary on the LEDs. So yeah, that was kind of good for just sort of, you know, I need to see, you know, you could use it like as a progress indicator, or like a debugging some sort of value, like what value, you know, did I compute out of this function, or, you know, update it to display a certain value. So like, did I get to this piece of code at all, or whatever. So for larger pieces of code, which was, you know, difficult to simulate using something like ASM80.com, then yeah, you could kind of use this to yeah, to sort of help debugging larger pieces of code running on the actual hardware. And then naturally everything was done using Git, because like everyone seems to use Git these days. But yeah, that also served as a like a backup mechanism as well, so I could check in all my code and upload it, making, you know, if my laptop decided to die or whatever, you know, I would still have everything. But also, you know, like, as you know, sometimes happens, you write some code and it works, and then you start making changes and then it breaks, and then you can't remember what it was that worked, and you have no more undo, you know, buffer in your editor, and you can't go back to the code that worked. So it was obviously, you know, it helps you get out of those situations as well. Yeah, and I think this might be sort of the last slide here now, but mistakes and assumptions and where to next. So yeah, I think using 7HC595 shift registers in the original driver board was pretty much a mistake. It needed way too many resistors to kind of do all the current limiting. You know, there's definitely better ways to do it. Had I used the TLC 5916s to begin with on that board, there's probably a good chance that I might never have actually rebuilt it using a CPLD. But I really kind of wanted to build a board with a, you know, do something with a CPLD, and you know, it's not too far from you know, sort of retro tech, you know, maybe mid 90s or something, but you know, it's not too far fetched, you know, to be using a CPLD in this. And well, I mean, it's not really actually meant to be you know, strictly retro anyway, but yeah, that gave me an excuse to do, you know, both use proper LED drivers and do something with a CPLD. I did make a big mistake actually with the IEI-IEO sort of interrupt chain. When I originally designed the hardware, I didn't actually really think about the, you know, the possibility of using something like an SIO to provide serial connectivity. So the board with the CTC on it was basically configured in, like, the hardware was basically configured to say, like, whenever the CPU starts, you know, the combination of signals to start, you know, reading or acknowledging an interrupt and reading a vector, when the CPU asserts those signals, just start outputting whatever the value is on the bus on the timer module. So if the SIO caused an interrupt, and then it would start to drive its vector onto the bus, the other board would just start driving it, you know, a value as well, and that would obviously result in some bus contention. And eventually I had to sort of settle, unfortunately, to using the SIO in polled mode, because yeah, I couldn't actually get these two things to play together. And back in Australia, I didn't actually have any tools like soldering irons or anything to fix it up. So yeah, that kind of that was a bit of a shame. But anyway, bit of head scratching moment there as well. But yeah, fixed that up, and the schematics actually that you'll find on GitHub reflect the fixed and corrected design to make these two play together. I made an assumption that ROM and RAM requirements would be a lot higher as well. So as you saw in the earlier slide, I only ended up using about 5.5 kilobytes of ROM, and I'd sort of allocated, about 24 kilobytes in the memory map. And in RAM, I think I used like less than 200 bytes of RAM, and I'd given it 16 kilobytes in the memory map. But that's not necessarily a bad thing, because it actually came quite, in handy. I could fit the entire image in RAM and still have plenty, left over to play with. So, it gave me the ability to sort of, build my software and then upload it into RAM and execute from RAM without having to worry about like, oh, I can only test, these parts over here because I don't have enough space to fit the whole thing in. Yeah, so next kind of steps are basically to, work the SIO board in sort of a more permanent way to use that with a GPS module for synchronizing time. And like PCBs and kits, like would anybody actually be interested in building something like this if it was available as a kit? And should I go to the effort of actually finally sort of laying this out onto PCBs and getting some made up and put some kits together? And yeah, with that, that's basically the end of it. It's quite a bit of a long talk, but there's some links here to my GitHub repo where you'll find like everything, like so all of the schematics, all of the source code, the source, like the Kupl source code for the CPLD, like that's all there. And then there's a second link there to a blog, which I set up to run through like the full sort of design process of the original clock. So you get all the photos and all the gory details of that. Yeah, so basically open up to questions.
Thanks, Tom. We've got a few questions on the chat, so I can go through those first, and then anyone has any more to ask. So one question was about your display board version 1 and why you use discrete resistors instead of resistor network modules.
Yeah, so a bit of a space constraint, I guess. You can kind of see here that the board is already really quite heavily populated. And actually, because I'm using common anode, I think it's common anode LED displays, so there's only one sort of power input, and then I'm syncing current into the 595s to turn the segments on. Yeah, I didn't have sort of room for dip style resistor networks, which definitely would have made things a lot easier, I think. There's probably, I don't know, like maybe if I'd squeezed things in a bit more, maybe I could have done it. But yeah, A, I didn't have any, and B, I don't actually think I would have had the space for dip resistor networks, and then SIP resistor networks wouldn't have worked either, because I've only got like a single anode pin on the displays. So yeah, I can't sort of limit the current that way. Yeah.
Because you used them before. You used them on the other board. You used the single inline resistor network, the yellow blob, the yellow thingies. I think you used it here. Exactly. Yep. So hey, you already have them. Why not use them? But
yes.
I think about the anode part, if that's really...
Yeah, like if I had sort of individual anodes and cathodes, I definitely could have used SIP style resistor networks to drive the displays. Yeah. But because you have like one common anode and then all of your cathodes are broken out, there's no way to sort of really limit like the resistor.
Yeah, I'm thinking too, but
yeah, maybe with open collector drivers or something that would have actually worked.
Yeah, well, this works
potentially as well. With common cathode, maybe. Yeah, there might have been a way to do that. Yeah. No, that's fair, yeah. So on this board, the SIP resistors are basically acting as pull downs for the inputs into the latches. So when the switch is in the on position, actually I can't remember if they pull down or pull up, but when the switch is in the on position, it's either grounding the pin or supplying 5 volts, and then the SIP resistor is, well, you know, the switches kind of act, I guess, like as a open collector type, you know, sort of setup. So when it's on, it's either grounding or plus 5 volts, and then the SIP resistor is kind of pulling it in that other direction, just as like a default. I think it's actually pulling up, yeah. So that's why I've got SIP resistor packs in there.
Okay, another question about time zones. Do you handle time zones changing on different? Sorry, summertime start and end. Do you handle summertime starting on different dates for different time zones?
Yes. So everything is sort of calculated as an offset from UTC. So, for example, if it's midnight UTC, and I have a time zone that is like plus 4 hours, then the way that it works is that it first adds on, and this is the 2-pass method, I guess, I'm using in my the clock app, but it'll sort of first add on the offset, which can actually be like basically a positive number or a negative number. So I can either add on, say, like 4, or I can add on -4 kind of thing. So I can add on 4 to get to whatever the time is in that time zone outside of daylight savings. And then I compare the time for that time zone against when daylight savings starts. And then if it's started, then I add on an extra hour via a second pass of the loop. I might have to reread some of the code to figure out exactly what he's doing, but yeah, it basically sort of works like that. So the first step is to add on the offset of the time zone, and then if the time that's being, or if that offset time is then within sort of like the start and end dates for daylight savings, then it will add on an extra hour. Yeah, I hope that makes sense. But it does handle, so for example, yeah, if it was, say, well, let's maybe use another example. If it's like 11 p.m. on, the 17th of December in UTC, and you have a time zone that's +4, by the time it's done all the calculation of adding on that +4, it will have already sort of worked out that the date of that time zone is actually, it's 3 a.m. on the 18th of December. And then if daylight savings was set to start at, say, 2 a.m. on 18th of December, it would then add on an extra hour, and it would sort of do that whole process again. Because if, for example, you're doing that at, say, 11:59, like the time in the time zone is 11:59, and you're inside the sort of start and end date of daylight savings, and then you add an extra hour on, well, then you sort of tick over into the next day, so it kind of has to recalculate the date as well. So it's yeah, I don't know if there's like better ways to actually achieve this, but also when you're trying to do this in assembly, it's yeah, you kind of need to break this down into like, simple, easy to understand steps. And I think this was kind of the best way I could sort of think of to implement that kind of a thing. Yeah. So I hope that answers the question. But, yeah.
Thanks. Yeah, I think one more question from the chat was, what about design interfacing or redesigning to work with the RC 2014 design?
Yeah, I had this question last time as well.
That was me. This time it's someone else. So.
Oh, right, okay. So I guess the honest answer is like, no, I never really had any thoughts about the RC 2014. Yeah, it's one of those things, like, I guess I kind of like to reinvent the wheel, I guess, in a way, but it's also my sort of way of learning. So, I designed all hardware, from scratch, using the knowledge that I've sort of attained over the last couple of years, and put it all together, based on, that sort of understanding. So the thought of sort of making it, designing it to work with the RC 2014 is not really something that ever crossed my mind. I'm sure you could come up with some modules, you know, that would plug into an RC 2014 bus, or, you know, something that would at least interface with an RC 2014 bus to make this work. And I'm also very sure that, you know, you could do this, what I've done now, like you could probably do that with a little bit less logic. Like there's a lot of stuff in here that's not duplicated, but could definitely be combined. Like a lot of the address decoding, you could, if you weren't trying to be so tight about how your you know, IO addresses were used, you could definitely do it with a few less chips. But yeah, short answer, no.
Okay, fair enough. So I guess one more question from me is, now you've built a Z80 system. I mean, how do you feel about in general how easy it is to do? Is this something you think that a relative novice with hardware could design the equivalent, you know, perhaps not a clock, but something else based around a Z80? Or did you think there's actually quite a steep learning curve to building something like this?
I found this actually to be a really interesting journey. You know, when I first learned about Z80, like way back when I was a kid, like I think, you know, there was probably a schematic in the magazine I was looking at, and I distinctly remember there being like, you know, a big page full of hex, you know, something you would have to type out probably and program into a ROM. When I looked at it back then, I had absolutely no idea what I was looking at, and I thought, like, you know, how on earth do even people come up with this sort of stuff, you know? And this might turn into a little bit of stories though, but yeah, like sort of a few years ago, well, when I was younger, I sort of had an interest in electronics, but yeah, as I said, like living on a farm in Australia, you know, you don't really have very many people around you. Getting access to information can be quite difficult sometimes. Like back in that day, you know, this is sort of, you know, mid 90s or late 80s. You know, I didn't have the internet. The first time I got on the internet was 1999. We had like 30 hours of prepaid dial-up or something, and once that was up, like, you know, we didn't get any more for like months, you know, later. So, you know, it was very difficult for me to really practice electronics back then as a hobby, just simply due to lack of information and access to people who actually, you know, could help me learn. My attention then kind of actually shifted towards software, because we had a PC and it had QBasic on it, and a friend had introduced me, or introduced that, or me to it, when I started high school, which I think you guys, well, high school for us in Australia starts in year 7, like, so I guess I don't really know how exactly that translates to the UK or elsewhere, but it's sort of like your, yeah, you sort of get out of your primary school days, so beyond, you know, your 6th year and that sort of thing. So I got introduced to sort of software programming, you know, sort of mid 90s, and having more access to, you know, to that, you know, we had a computer with QBasic. I could practice on that every day, and, you know, I could get books relatively easily from the library at school, or, you know, my mum bought me a couple of books as well. You know, so I was able to learn a lot more about that. It wasn't actually, you know, skipping forward quite a lot of time then, because my interests kind of varied a lot as well. Like, you know, the early 2000s, I got into, you know, network engineering and telecommunications and that sort of thing. So there's kind of a big gap between, you know, electronics and software, and then, you know, ending up where I am now. But it was sort of, yeah, maybe 2016, 2017, where I was like, hang on a minute, like we've got, you know, basically the internet is built into our lives now, and there's like so much more information, like on YouTube, you've got websites and all sorts. Yeah. So that's really where things started to pick up again for me in terms of like my interest in electronics. And yeah, so I was then able to actually find more information about, you know, how things like the Z80 worked. You know, I could look at schematics for, you know, computers and like that were built with them, and actually understand what they were doing now, because, you know, so that, yeah, that all sort of really picked up. And I don't know, like, I mean, everybody's journey is going to be a little bit different, but I found it like incredibly easy to pick up the concepts about how, you know, the process of works, how to interface it with all the peripherals. Some people may not find it as easy. I think, yeah, I don't know if it's like my background, the exposure that I've had to, software and, stuff like that, but I've just found it, yeah, like incredibly easy to actually, pick all of this stuff up and, just sort of going through, the images in here, like, like looking at all of the stuff that I've thrown together to actually make this work, it's, some people might look at this and think it's actually quite impressive, really, that, in maybe the space of 2 or 3 years, you can pick up the amount of knowledge you need to be able to build something like this. Yeah, so a bit of a long-winded answer, I suppose, but I think it's going to depend a lot on, just your natural ability maybe to understand technical things, how easily you're able to absorb that information, and yeah, like that. I think that's probably maybe the best answer I can give. So yeah, some people just seem to latch onto this stuff a lot more easily than some others might want to be able to. So yeah, and yes, demo would definitely be a good idea, since that's sort of half of what we're here for, I guess. So this is this is it here at the moment. I've sort of got basically the full complement of boards installed at the moment. I'm actually powering it through the SIO board, but yeah. So actually, I didn't really explain on this board here what these switches and buttons and stuff are doing. So there's a very basic sort of button-based interface. There's like essentially like an enter button, an escape button, and then an up and a down button. So you can sort of navigate through menus. You can adjust values and sort of set values and that sort of thing. And then the switches are used for configuring what's being displayed on each row of the display. So basically, I've used one of the switch position 8, I think, which is the most significant bit, to sort of indicate whether or not what's being displayed on a line is a date or a time. So with the switch in the on position, it's a date, and with the switch in the off position, it's a time. And then that sort of, I guess, basically gives you the option to select between, 128, different time zones that you could then have in the ROM. There's actually like a little 4, there's a little 4-position switch that's missing from the top row there, which I added in, and that sort of allows me to just change a couple of little options, like how much dimming do I want to have, like 25% versus 50% duty cycle or something like that. And I think there's a couple of other little options that you can select using that. But yeah, like the effect that I was kind of explaining earlier, like if must be this button, if I hit the escape button, essentially, I can sort of, I can go into the configuration app and I can kind of go between, date and time. If I want to set that, I can kind of, go through and, cycle through, the various options for, configuring hours and minutes, and then, years, months, etc. And then if I exit out of configuration and go to the clock, you sort of get that kind of like almost like a rippling kind of effect as it's sort of updating the display. And that's kind of like, a little sort of effect, I guess, that I borrowed from the DISC-y interface on from the Apollo era. So it looks quite cool when it sort of updates and it just sort of sort of cycles through and fills everything in. Yeah. So yeah, very brief, quick demo there, but yeah.
Cool. Thanks, Tom. Any other questions?
Thanks, Tom. I need to go. I have some daughter to bring to bed. So thanks for the demo and the explanation. Looks like an amazing amount of work, and I'm never going to replicate it.
I'll just I'll jump back over to the last slide there. I mean, if you want, feel free to contact me via GitHub. I'm also on the RetroComp mailing list if you're part of that, or you can probably even get me through the meetup group as well. So yeah, cool. Feel free to reach out.
Thank you. Good evening.
Bye.
Bye.
Yeah.
Anyone else have any questions?
I think we had one last time about the price of a kit.
Ah, yes.
Yeah, so if I was going to build a kit out of this, I think I'd kind of estimated that the price might be something like £200. I still don't really know exactly what it would be, but yeah, I did actually have a look at, for example, JLC PCB, who I've kind of been using lately as my preferred manufacturer, and actually even like a 4-layer board at the size that these are like 12 centimeters by 18 centimeters, wasn't stupidly expensive. So I could probably potentially sort of, downrate that estimate a little bit. But yeah, I'd say maybe somewhere between 100 to 200 pounds for a kit. But honestly, it's a guess at this stage. So yeah, don't quote me on that. But yeah, definitely, if anybody would be interested, yeah, let me know and I'll see if I can put the time into it.
Cool. Thanks, Tom. And again, thanks for doing this a second time. It really is much appreciated.
Hopefully it was a little bit more coherent this time. I had a little bit of extra practice for it. So yeah.
Okay, I'm going to stop the recording now. And I guess if anyone wants to hang around for general chat or anything else, then we're free to do that.